Hi guys, welcome back here at DC Engineering Tutorial. So this time, let's continue our discussion on water flow measurement. So let's talk about flumes. So ito yung itsura ng mga flumes. So flumes are specially shaped engineered structure used to measure the flow of water in an open channel. So flumes are static in nature, having no moving parts, and develop a relationship between the water level in the flume and the flow rate by restricting the flow of water in various ways, no? Flumes can accelerate slow, subcritical, bali yung fluid number is less than 1, or supercritical state, bali yung fluid number is greater than 1, by a change in elevation, a contraction on the sidewall, or the combination of two. Accelerating slow flow to a supercritical state creates upstream condition where under free flow condition, that the flow rate can be determined by measuring the water level at a single defined point in the flume, say HA. So next slide is so most flume styles consist of three parts. We have a convergence section, which is the inlet, a throat, and a discharge section, which is the outlet. So ito yung sa inlet na part, converging section. So the flow is restricted in the converging section and is accelerated as it passes through the throat. So flow in the convergence section must enter at subcritical state, typically with a fluid number no more than 0.5. So it is here that the point of measurement HA is located. So dito natin nakukuha yung value ng HA. So dito sa throat naman is accelerate the flow to a critical or supercritical state. So dito sa discharge section or the outlet, slows the now energetic supercritical flow and transition it into a downstream channel. While not all flumes have this section, such as H and Montana flume, the lack of this section means that the resistance to submergence is limited and that the downstream channel may be susceptible to scar and erosion as the flow spills off and the end of the flume. So the advantages of flume is this instrument is effective when the total head drop is small. So its operation is independent of approaching velocity, and being a self-cleaning device, it is not affected by sand or salt deposition, unlike sa wear and orifice, no? So classes and style of flume. So in the approximately 100 years since Dr. Parshall began his investigation in his improved venturi flume, two distinct classes and numerous styles of flumes have been developed. We have the short-throated flume. Short does not refer to the flume length, but to the fact that the flow is controlled in a specific region of the flume to produce the level to flow relationship. So example of short-throated flumes are partial, Montana, or modified partial, the USGS portable or the modified partial, the HSHL trapezoidal, and the cutthroat. For long-throated flume, long-throated meaning controlled flow in the throat that is long enough to cause parallel flow lines in the section of flow control. No? Example of that is the Polymer Bolus flume and the RBC Flume. Okay, so ito yung mga example ng mga short-throated flume. We have the partial, Montana, USGS portable, HS, H, and HL. S stands for small, L stands for large, trapezoidal, and cutthroat. And for long-throated flumes, these are yung mga dagway, no? So we have Polymer Bolus, ito yan. And we have the RBC. So yun yung mga mukha nila. Okay, so isa-isahin natin yan. So partial flumes. So while working at the U.S. Soil Conservation Service, Dr. Ralph Parshall saw a need for more accurate measurement of surface water, no, particularly irrigation and water rights flow. At the time, wear and venturi flumes were used to measure the flow rates, but both devices had shortcomings. So starting in 1915 with a subcritical venturi flume, Dr. Partial made a series of modifications, ultimately leading to his improved venturi flume. So the critical improvement that Dr. Partial introduced was a drop in the floor in the throat section of the flume. So the constriction of the throat creates the head to floor relationship. So by sloping the floor down here, the resulting flume can withstand relatively high degrees of submergence without affecting the flow rate. A short-throated flume, only one depth measurement is needed. Calculate the flow rate through the flume, greatly simplifying matters. So 6 years after his work began, Dr. Partial filed a patent for his new partial flume. So a partial flume is a fixed hydraulic structure used to measure the water flow in an open channel or non-full pipe. So the flume accelerates flow by both a contraction of the parallel side walls and drop in the throat's floor elevation. So the contraction and drop accelerates the flow from a slow subcritical state to a faster supercritical one. So the transition is similar to the transition in air from subsonic to supersonic regimes. So yun yung partial flow. So these are devices for the measurement of flow of water in an open channel. When the depth of flow is less or the head drop is very small, and the volume of flow is less and the channel bed is less. So, yan, makikita mo yan, no? Yan yung itsura ng partial flume and ganito mag-react yung water natin. So, the flume consists of a convergent section with a level floor and a wall converged towards the throat section. A throat section with a downward sloping floor and a parallel walls, and a diverging section with an upward sloping floor and a diverging walls toward the outlet. So the size of the flume is determined by the width sa throat natin. So the size ranges from 7.5 cm to several meters in the throat width. Okay? So bali yung naming ng mga flumes natin is andun sa width ng throat nila. Okay, so these are available in various materials. So very small, we have 25.4 mm to 76.2 mm. Pag small, 152.4 mm to 2,438.4 mm. Pag large, 3,048 mm to 15,240 mm. So partial flumes may be built of wood, concrete blocks, concrete, and bricks, or in smaller sizes of heavy sheet metal. So ito naman yung plan, parang plan na ano niya. So meron tayo ditong aerial view and elevation view and section view ng partial flume. So dito sa table, makikita natin yung mga dimension and capacity ng partial flume of various sizes. Ayan. So depende kung ano yung throat width niya. Then we have this dimension, no? Makikita mo yan dito sa plan. May mga ABCD kasi yan, no? So dito natin makikita sa table. And we can also calculate the discharge using this table, no? Like susukatin mo lang yung head ng tubig doon sa flume. Then alam mo yung throat width ng flume. So like mako-compute, for example, meron kang head na 8 cm using a 7.5 cm na flume. So meaning, meron kang discharge na 3.4. Di ba? So ganun lang. 3.4 liters per second. Okay? So may chart tayo for partial flumes. So for free flow, bali yung Q is equal nung C multiplied by H raised to the power of N. Yung Q is the discharge. Yung C and N are flume coefficient which vary with the size of the flume, and H is the measuring head. No? Partial flume coefficient chart gives Q in cubic meter per second and H in meters. So ito yung partial flume coefficient. But we can also use this tabulated table, no? Which gives a set of standard values for C, N for different dimensions. These coefficients are in feet per second units, so the calculated discharge would be in cubic feet per second, and head has to be in feet. Okay? So dapat ito is naka-English unit while itong chart is naka metric unit. So we have also submerged flow, which occurs when the hydraulic jump is not visible at the throat. So that is when the downstream head is sufficiently high that it drones out or shallows up the hydraulic jump. So in our calculation, submerged flow occurs when h over h is greater than 0.6 for b, which is less than 3.05 meter, and h over h greater than 0.8 for b, which is greater than or equals to 3.05 meter. So for submerged flow, the ISO equation 12 is rewritten as Q CHN minus QA, where C and N are found from the above figure based on with QA accounts for the effect of submergence. So bali yung equation ng QA natin is given dito. Okay? So makita mo dito na yung Q is CS times Q3. Yung Q3 is dito yan natin makukuha sa graph. Itong submerged partial flume graph. Okay, so let's watch this short video on how to use the partial flume.
Today we're going to talk about partial flumes, how they work, how to get an accurate measurement from them, and whether or not they are properly functioning. So the first thing we want to do is identify the size of the partial flume. And we know this is a partial flume because we have this contracted throat section here in the middle, which is characteristic of all partial flumes. Now these types of flumes always have a converging section with a flat floor. Water moves through a crest, through that throat section we talked about, and then out a diverging section to the end of the flume. So when we walk up to a flume in the field, we want to always make sure that water is going down the flume and not around or underneath the flume. So a quick visual inspection at the top end of the flume will let us know if that water is actually moving through the flume. Also, we want to make sure that water is moving somewhat even and tranquil as it enters that flume, and it's not a high turbulent flow. Okay, now that we've established that we have a good approach to this flume, that the flow is tranquil, another aspect of ensuring that we have proper functioning condition in this partial flume is to make sure that we are in a free flow condition. And that's pretty easy to tell in a partial flume visually. If you have a standing wave, like we're looking at right here in the throat here, if you have a standing wave that exists, a frothy wave across the channel, that's an indication that you are in a free flow condition. Ideally, you would like that standing wave to be somewhere below that throat section, but in this case, it still looks like it's in free flow. As that wave migrates up flume, it'll start to submerge the flume, and at that point, you will no longer be in a free flow condition. Okay, last thing we want to check to make sure this is a properly functioning flume is the level. These things have to be put in level, and typically you'd like to check your level on the floor of the flume as it approaches that crest. That's not always possible when you have water. So what I typically do, and I like to go right across the throat of the flume, I'll just set my level down across the throat, make sure that it's level, and then also do it lengthwise. Find a good spot you can put the flume lengthwise to make sure it's level, and then we're good to go. A couple things about staff gauge with partial flumes to ensure you're getting an accurate measurement are, first of all, that the staff gauge is actually on the bottom of the flume itself, and then it is placed a distance of 2/3 up from the crest of the weir to the beginning of the flume. Okay, so now that we have made sure that this is a properly functioning partial flume, last thing we want to do is get our discharge measurement. We need two things for that to get a discharge measurement. One is we need to know the size of the flume, and secondly, we need to know what the stage is, or the staff gauge reading of the water moving through the flume. So to determine the size of the flume, for partial flumes, they're always designated by the width of the contracted throat section here. In this case, it's 1.5 feet. And then we just simply take a reading off the staff gauge. It's always in feet, intensive feet. In this case, it's 0.51 feet. We looked that up on our rating table. Could be from a manual, could be an online table that you get for a 1.5 foot partial flume. And in this case, our discharge is going to be 2.13 cubic feet per second. So the 4 things you want to check when you're using a partial flume are to make sure that water's not flowing around or under your flume. Make sure that the flume is level lengthwise and crosswise. Make sure you're in a free flow condition, and make sure that your staff gauge has been properly placed.
Okay, so we have also USGS, Portable Partial Flume. So ito yung itsura niya. So Johnson provides the discharge equation for that flume, which is 1.142 HA raised to the power of 1.58. So the USGS Portable Partial Flume is a modification of the standard partial flume where the discharge section has been removed. So the purpose of the modification is to reduce the weight of the flume and to make it easier to install. So this modified design was originally developed by Troxel and Taylor for the use in Southern California. It's originally described as a Venturi flume in March 10, 1932 memorandum from the Office of the Groundwater Branch, USGS. The flume was little used until Taylor's paper, Portable Venturi Flume for Measuring Small Flow, was published in May of 1954, and that the flume again came to the attention of its potential user. So the original design of the 3-inch flume had a reduced sidewall height of 6 inch, but was later increased to 9 inch to provide additional freeboard in the flume. So the initial rating of the flume took place at Colorado State University Hydraulic Laboratory in 1931, while the redesigned flume was checked at the Hydrological Laboratory of the USGS in Denver, Colorado. So aside from that, we have also trapezoidal flume. So trapezoidal flumes are somewhat similar to partial rectangular flumes, as shown here in the figure, the details of the trapezoidal flume. So the head and discharge relationship are shown in the figure. So based on the study, the characteristics follow. We have 1 to 8. Number 1 is we have this extreme approach condition seen to have a minor effect upon the head discharge relationship. Number 2 is material deposited in the approach did not change the head discharge relationship noticeably, and so on and so forth, no? Hanggang 8, which is since a small change in head result in a comparatively large change in discharge, the sensitivity of the flume changes in discharge is less than that of the rectangular flume. So another type of okay, so before that we have the details for trapezoidal flume, and the dimensions are in inches except as shown. So we have this plan view, young throat, young profile, and the end view. So we have also the calibration curve used for trapezoidal flumes under the free flow condition. So we can use this chart for calibration. And we have also Cutthroat Flume. So in the 1960 researchers at the Ottawa Water Research Laboratory began investigation into what we become the Cutthroat Flume. So the researchers' goal was to develop a flume that overcame the limitation of the partial flume in a flat gradient application. So rectangular Cutthroat Flume are available in 4 different lengths. We have 18, 36, 54, and 106 inches, and 4 cutthroat widths for each length. So trapezoidal cutthroat flumes come in 3 different throat widths. Okay. So this flume have a distinct advantages over a similar flume in that for a given length, intermediate throat widths can be developed without the need to laboratory or field rate the new flume sizes. So the importance of not needing the rate or re-rate a new size cannot be understated. So these are the details for the cutthroat flume. So the geometry of the throatless flume with broken plane transition was first developed by Punhab by Harvey in 1912. So in the cutthroat flume, however, The flume discharge and the modular limit are related to the piezometric heads at the two points in the convergence section HA and in the downstream expansion HB. So one of the advantages of the cutthroat measuring flumes is that there are only two walls on each side, resulting in the economic installation. No? So mas mura ka, di ba? So the cross section can be rectangular, trapezoidal, or triangular depending only on the availability of the appropriate calibration. So the U-shaped section can also be used for critical depth flumes. So yan yung details ng cutthroat flumes. So the formula used dito sa cutthroat is we have C1 HA raised to the power of N multiplied by L. Yung CA is the flow rate, yung C1 is the free flow coefficient, which is the value of Q when HA is 1 foot. Yung N is the exponent whose value depends only on the flume length. Okay, L. Bali yung L is yung flume length. So we have also Montana flumes. So the Montana flume, ito yung itsura niya. So it is a modification of the widely used partial flume. So the flume takes its shape from the hourglass of the partial but omits both the throat and the discharge section, leaving only the flat-floored convergence section. With the deletion of the throat and the discharge section, the Montana flume requires free spilling flow off the end of the flume. So the Montana flume is restricting structure that accelerates flow through the contraction of the parallel side walls. So locking the throat and discharge section of the partial flume flow out, the Montana flume spills directly out of the end of the flume. So the contraction and spilling discharge accelerate the flow from a slow subcritical state to a supercritical one. So as a result, the flow can be accurately determined in the upstream convergence section of the flume by taking a single depth reading at the specific point of measurement. So aside from Montana, we have also the HS, H, and HL Flume. So the dust bowl experienced by the United States during the 1930s, so the establishment of the Soil Conservation System, or the SCS, on April 27, 1935. So the SCS was established as a permanent agency, the U.S. Department of Agriculture, with a mission to conserve the nation's soil and water resources. So with this mandate, researchers at the SCS began investigation and the development of the class of flume suitable for the use in measuring agricultural flow. So ito ginagamit for agriculture. Ito yung itsura niya. Yan. So the H flume, so called because it was 8 in the series of flume investigated, combined the flow sensitivity of the narrow angle V notch wear with the flat floor and self-cleaning properties of the flume. So the H series of flume are more modified wears than the R true flumes with V-shaped throats and no diverging discharge. So the H flume design allows a wider range of flow than any other flumes type, provided low flow sensitivity as well as the ability to measure high flow rates. So meron siyang mga version. We have smaller and a larger H flume. No? So S stands for small h, HL stands for large h flume. Okay, so another type is the Polymer Bolus Flume. Unlike most other flume style developed for irrigation flow and then applied to other uses, the Polymer Bolus Flume is specifically designed to measure the sanitary sewage and wastewater flow from the outside. So these are used for sanitary and wastewater. So the Polymer Bolus Flume is widely used to measure the industrial discharge, the municipal sewer flow, and the influent at wastewater treatment plants, and is second only to partial flume in popularity. So designed for installation in existing manhole channels, such as shown here, and in line with the sewer piping, the Polymer Bolus Flume have a U-shape na cross-section as shown here to minimize the transition of flow through the flumes. So a raised trapezoidal ramp section creates the throat of the Polymer Bolus Flume. Okay? So makikita mo na pa-increase siya, no? Dito. So as the floor of the flume rises, the side walls also contracts. Another type of flume is itong RBC Flume. Ito naman yung itsura niya, naka-trapezoidal. So a class of affordable long-throated flumes, the RBC is relatively recent, 1984 flume, developed to measure the flow in the earthen channel. So for mga earth canals and furrow maganda gamitin yung RBC. No? So, follow by the researchers at the US Department of Agriculture and the International Institute of Land Reclamation. Name for its developer is Ripley, Boss, and Clemens. That's why it calls RBC. Na? So, in a series of 5 different flumes intended to be highly portable, easy to make, and extremely accurate. So, the RBC flume has a constant truncated V shape, allowing it to conform to the typical shape of the furrow and irrigation channels. So, the throat of the flume consists of a slope ramp similar to the Polymer Bolus flume. As the long-throated flume, the RBC flume can be designed and calibrated using computer analysis. So this analysis eliminates the need to laboratory or field rate new or non-standard RBC flume sizes with excellent accuracy. Like its shortened throated Britain, the trapezoidal and cutthroat flumes, the flat floor of the RBC flume makes it less expensive to install or retrofit into existing channel. As with the other long-throated flume, the RBC Flume has a high modular limit or submerged transition of 90%. Okay, so I think that's the end for Flume. So in the next video, we'll be discussing on area velocity method. Okay, so keep on watching and see you in the next video. Thank you.